Why do rivers still show PFAS contamination decades after the source was shut down? To answer that, you first have to understand what these molecules are and how they move through the ground. Then we can talk about simulating them. PFAS are chains of carbon atoms wrapped in fluorine. The carbon-fluorine bond is the strongest single bond in organic chemistry, around 485 kilojoules per mole. Sunlight doesn't break it. Microbes don't break it. Ordinary water treatment doesn't break it. So unlike almost every other contaminant we model, PFAS does not decay away. Mass that enters the ground has to go somewhere, and the only question is where and how long it takes to get there. The first control on that journey is sorption. PFAS molecules stick to organic carbon and mineral surfaces in the soil, then release again. Sorption follows a Freundlich isotherm. Sorbed mass rises with concentration, but not in a straight line, and it is compound-specific. PFOS, with its long chain, binds strongly and creeps downward. PFBA, a short chain, barely binds and travels almost as fast as the water itself. Same spill, same soil, two completely different arrival times. The second control is the vadose zone, unsaturated ground between the soil and the water table. Its travel time is depth times water content times retardation divided by recharge. Through 3.5 meters of sand, a pulse arrives in a few years. Through 30 meters of till, the same pulse takes decades. This single ratio explains why one contaminated site shows up in groundwater almost immediately, while another stays quiet for a generation and is still loading the aquifer from spills 50 years old. Once mass reaches the water table, two processes take over. Advection carries it along with groundwater flow, typically meters per year, not per day. Dispersion spreads it, smearing a sharp pulse into a long, dilute plume. And where the aquifer meets a gaining stream, that plume discharges. This is the step that answers the opening question. The river is fed by groundwater that was contaminated decades ago and is only arriving now. Which raises the question this whole field turns on. Why model any of it at watershed scale? Because a monitoring well tells you one point at one moment. The contamination does not stay there. It runs off the surface, it travels down gradient through the aquifer, and it collects in the stream network. And the people exposed are somewhere else entirely. A drinking water intake, a wetland, a fishery, kilometers downstream. Surface water is not an optional add-on to a groundwater problem. It is where groundwater ultimately discharges, where contaminated runoff arrives, and where exposure actually happens. The watershed is the smallest unit that contains the whole pathway from source to receptor. Model anything smaller, and the answer leaves your boundary. So how do you compute all of that over a whole watershed for 50 years? You can't. Off the shelf, standard SWAT Plus has no PFAS fate and transport. We developed it from the governing physics and the empirical relations you just saw, Freundlich sorption, compound-specific leaching, and implemented it inside the SWAT Plus engine. Then, for the subsurface, two models are coupled. SWAT Plus computes the land phase, rainfall, runoff, soils, crops, and channels. MODFLOW 6 computes the saturated zone, the vadose zone, and solute transport. They advance through the same daily loop, exchanging fields and memory through MODFLOW's programming interface. The exchange runs both ways, and the return direction is the one that matters. SWAT Plus sends down percolating water and the PFAS mass leached from the soil. MODFLOW 6 sends back the water table, the groundwater discharging into each channel, and the PFAS mass that discharge carries with it, computed as base flow times groundwater concentration. In a 90-day coupled run of a legacy plume, that path delivered 44.7 kilograms of PFAS into the stream network. That is the loop closing, soil, to vadose, to aquifer, back to the river. Here is what that looks like on a real site. A former Air Force base in Michigan, where firefighting foam was used for decades. Watch the simulated plume leave the source area, sink below the water table, travel with groundwater flow, and reach surface water. And here is how we know whether the simulation is right. 35 monitoring wells at that site carry over 4,000 publicly reported PFAS measurements. Plot them against depth and the fingerprint of legacy contamination appears. The highest concentrations are not at the surface. They sit buried near 60 feet, mass that left the soil decades ago. Any coupled model worth trusting has to put the mass down there too. From a molecule too strong to break down, to a plume arriving in a river 50 years later, every step of that journey is physics. And physics can be computed.